So welcome to this penultimate session of ADAS 2020. We're going to start with an invited talk by Melanie Krips, who is now, since 2017, has been NOEMA scientific coordinator, and she's been with IRAM, well, for more than a decade now. First as a postdoctoral fellow and then as a permanent staff, and now she's, as I said, scientific coordinator for NOEMA. And she will tell us how 1 million lines of code make the optically dark universe visible. So please give a round of applause at homes, and the floor is yours.
Okay, yeah, hi. Thank you all for your interest in my presentation. As already said, I'm Melanie Krips, so I'm the scientific coordinator of NOEMA. So my role is to make sure that there's a smooth process from the first submission of a proposal until the final delivery of the data. So from the whole proposal submission process to the reduction of the data. And so as you can imagine, I'm an astronomer, not a software engineer. So my idea of this talk was to give a general overview or the global aspects of this whole process with a bit of a focus of the pipeline, as the session is about pipelines. So it's a pure astronomer point of view, so I will not go too much into the technical details. And here's the outline of the talk. So of course, I want to start with the motivation, why we are doing all these efforts to going through all the technical and software challenges to get the final data products. Then what is NOEMA? I'm briefly presenting our instrument. And then I want to talk a bit more about the whole working flow from the first ideas up to the actual maps. That includes to understand a bit the requirements, what are our constraints, what is the framework that we are working in. A brief historical overview as well, because we have recently in the past few years, as some of you might know, we have been going through a huge upgrade phase. So we have almost doubled our antennas, bandwidth, and observable bandwidth and everything like this. So this is a huge effort. And then I want to present, of course, also a bit the pipeline that we are currently using. So the motivation, why are we doing this? So it's a millimeter radio interferometer that we are using. So this is an optical picture of the Horsehead Nebula with the famous Horsehead. We see a lot of optical emission, but a lot of optical dark places as well. And actually, if one starts to observe at different wavelengths, so going to the longer wavelengths to the radio domain, we can actually see that these dark places are full of emission, but which are only visible through other mechanisms like emission from molecular gas that you can see here. And actually, this is a picture from the 30 meter that's in Granada, so where the host is located. We can see that's full of emission and structure and yeah, a lot of information. So this was a nearby galaxy, but I also want actually to show a map that's coming from NOEMA. So this is a spiral galaxy M51, and you can see again in the optical dark places, you can see all this emission that's coming, in this case, from a CO. This is a map. This was a huge project a couple of years ago actually at the time, which is called Plateau Bure Interferometer. Yeah, so we are looking at oftentimes at areas that are, as I said, hidden in the optical. So we are getting in complementary information. These areas are often places of stellar bursts, or there can be galactic nuclei, so close to black holes that are creating material from their environments. Or these can be a lot is now observed in galaxies at very high redshifts, so from the very early universe, which is important to understand galaxy evolution and cosmology and stuff like that. So these are the main areas that we are observing. And of course, we do not only get maps, but also, forest of lines that we can observe. So this is a line survey that was also actually done with a 30-meter more than 14 years ago by Sergio Martin. So there's a lot of spectral information as well that we want to get at the same time. So these are kind of the motivations for us to do these observations with NOEMA. So what is NOEMA? NOEMA stands for Northern Extended Millimeter Array, which was formerly called IRAM Plateau Bure Interferometer. At the time, so more than 5 years ago, we had 6 antennas. Now we are having 11 antennas, the 11th antenna, so we have almost doubled the number of antennas now. Has been recently commissioned in September. The 12th and the last antenna for NOEMA, or at least for the moment, is currently under construction. NOEMA is located in the French Alps. So the headquarters of IRAM is in Grenoble, and the Plateau de Bure, where the actual interferometer is about 100 kilometers to the south from Grenoble at an altitude of 2,500 meters. And just to give you the basic numbers, so we can move those 11 or soon next year 12 antennas around they have a distance between 50 meters, which is the size of the dishes actually, up to currently 760 meters. But we also have a project to extend this to almost 2 kilometers or 1.5 kilometers. We currently are using those antennas in 3 different configurations, which offer at the highest angular resolution of 0.1 arc seconds at the highest frequencies. And we have, since a couple of years, a new powerful correlator, which is called Polyfix, that offers 32 gigahertz instantaneous bandwidth that actually split up into 2 polarization over 2 7, almost 8 gigahertz wide sidebands. So now coming to the whole workflow. So as you know, you first need an astronomer who has a nice idea that then submits a proposal. We have 2 deadlines every year through a proposal submission management system. Once this has gone through the PC, so proposal committee, now I'm missing the word. So the program committee meeting, and once the proposal is accepted, we will go to the observing management system, which includes to actually help to observe, to set up the observing scripts. Then everything is fed into a scheduling system, which we are currently using a status manager, which helps to prioritize the projects and make this visible to the operators and the astronomers on duty, which actually schedule then and observe the projects, which is shown here. This is one of our colleagues, one of our postdocs. Then once a project is observed in one track, which might not be finished, then it's actually running through our pipeline that does a data reduction that includes monitorings and a first quality assessment, which is then done by the astronomer on duty with the help of several assessment scripts. And then that information is fed back into the status manager, which helps to decide whether a project has to be continued observing because it's not done yet, or whether it's done. And then when the whole project is done, the PI will be informed, and then there will be a final data reduction because there may have been several tracks that have been observed throughout the semester, which is about 6 months. And you want to make sure that the different tracks are consistent with each other. The different reduction, they are actually done with the same version of the data of the pipeline reduction software as well, because they can cause differences as well, especially right now we are doing a lot of upgrades. Oops, I don't know why it's not. Okay, sorry, I don't know why it didn't forward. So this PMS and OMS systems that were actually mainly developed by one software engineer who is actually just working 2 days a week. But this is a fantastic system that has helped us a lot in the past few years to deal with all the proposals and everything. So just to give you a look, so it's a pure web-based system where you can upload your abstract, your title, your scientific justification, and all the technical details that are necessary to fulfill the goals that you want. Once the project is submitted, you will get all the information about the PC system, so the grading and stuff like this. and you can visualize so the setup, frequency setups of your system, your source and everything. And then once the proposal is accepted, it will go through this observing setup system or management system. So I blacked a lot of stuff because it's a proposal from the current semester, but I wanted to show you how it's looking like. So it's a really amazing and very useful system for PIs and also for us to manage all of the information that are submitted by the PIs. So all of this this is fully web-based. For now, so the final idea is actually to have a full system that goes from proposals to the delivery of the final data products. So that's still a big project in progress. Sorry. So while the first two parts that have been fully developed by, of course, with input from the astronomers, but by the software engineer. So you can see it's very professional. It's very nice as well. It's a very powerful system. While the remaining, so from scheduling up to the final data reduction, that's mainly has been developed by astronomers, also with the help in some parts by software engineers, of course. So it's much more goal orientated than actually the techniques, because we are all not software developers, which also has its advantages, of course. So the scheduling, the status manager, for instance, that's based on the Python script. And now for the final, for the remaining time, I would like to concentrate on this lower part from the observations to the pipeline to the final data products. So just to come back to the interferometry, so why we are using interferometry, why we are using several antennas and not a big dish. So the radio astronomy is based on long wavelengths. And to get a high angular resolution, the antennas have to be much, or the telescopes have to be much bigger in diameter than like optical telescopes. And of course, you can only build up a telescope up to a certain diameter. So starting, up to 100 meters, more or less, that's still technically feasible. Otherwise, they're getting too big and then everything would be collapsing. And another aspect is as well that you need a large, very accurate surface, especially at the millimeter wavelengths that we are observing at. So it's of the order of tens of micrometers. And that you cannot do with 100 meters. So at 10 to 20 meters, that's still doable. So the technique that we are doing, we are actually spreading using several antennas that are connected together to simulate a huge antenna that can have several hundreds or even kilometers of baselines, which then would correspond to the diameter of a simulated single dish. But of course, an interferometry is a much more complex technique than a sub-millimeter or millimeter single dish observation. So there are many more technical aspects that go into this, which makes it very complicated. So just to show you, if you observe with a single dish at millimeter, like the 30 meter in Granada, what you will get, of course, you have all the front end equipment, the technical equipment with receivers, which goes to a backend, so to actually digitize your spectrum. And what you will get is a spectrum out of the area. If you just do one pointing in your favorite source, you will get out a spectrum. Now, if you go to interferometer, you will correlate the signals that are coming in at least 2 dishes or more, preferentially, of course. You have the same receivers, but then you have a backend that is much more complex that goes through a correlator. And then you will not only get the spectrum, but also the map. And actually the distribution of all the, not quite instantaneous, that's not quite true, but a whole map. So as I indicated, we have been going through a project of a huge upgrade of the former Plateau de Bure interferometer. It started in 2007 already with a new generation of receivers. So an IRAM, the interferometer, is around since the early 90s when the first antennas were built and when they started the interferometry. Since then, most of the stuff we have the software that we are using has been written in-house, which is called Gildas. And we were using a lot of widgets and a lot of or byte typing comments to reduce data. But with the new set of receivers, it was realized that this is not feasible anymore. And that actually, so we kind of had a pipeline before, but there it was really clear we needed a real data calibration pipeline. And then when it started. And then with the arrival of Widex, a new correlator that actually allowed to, so before we could sample a spectral bandwidth of about, well, less than a gigahertz, was actually, I think, half a gigahertz, which is shown here with this small blue tray that was before. And then with Widex, we more than doubled then we went to 1.6 gigahertz. So we could already start sampling, but of course, astronomers always want more. Yeah, and we're always interested in getting the most of the lines as simultaneous as possible. That's why we went when we started. So the upgrades to NOEMA started in 2015 when we got a 7th antenna, and again new receivers. Then antenna 8 came, and then the old correlator was able to correlate up to 8 antennas. So anyway, to go to 12 antennas, we were needing a new correlator. And that's when Polyfix came, which actually then not only, so before we had half of this bandwidth, now we doubled this, and we were also able to use both sidebands, not just had to decide for one of the baseband and suppress the other one. So we can instantaneously cover 16 gigahertz in 2 different sidebands, and then we just have to do two tunings or two observations to get then 32 or more gigahertz worth of bandwidth, which is of course very powerful and means a huge step forward in many different aspects, but also that means so not only we can cover this whole bandwidth, but at a given fixed spectral resolution of 2 megahertz, but also we are able to set several smaller spectral windows at a much higher spectral resolution, and we are working on more modes for this powerful correlator. So not only we have more spectral information, so the data size increased rapidly, but also with adding more antennas and the new correlator, we got a lot more sensitivity. So we gained 100 times in sensitivity and an order of magnitude also in for line observations. So as I said, the interferometry is very complex. So the requirements for what we need the pipeline to do, which is of course coming a lot from my perspective as a coordinator. So we want it to calibrate the data, obviously. So do the reduction of the data in a reliable and of course reproducible way, and also in a reasonable amount of time. So before it was running like 10 or 20 minutes, but now with the huge increase of data sizes, the specifications were that it remains under an hour. So that is mostly for the astronomer on duty to have a quick and robust assessment of the quality of the track. We also wanted to provide monitoring of the technical performance of the interferometer to be able to do quality checks and also to understand whether there are problems, because it's since it's a very complex instrument, there are so many ways where it can go technically, we can have technical problems. So it's very important for us to have a quick check and a quick look at the raw data and technical aspects of the interferometer to have an idea where the problem is coming from. Is it coming from one of the antennas? Is it coming from the correlator? It's coming maybe from the cables, or there are so many different things that can actually go wrong that we need a quick access of the data. It's also supposed to highlight problems in the track in an automatic way. So to already recognize if there's something wrong with the data, that's not supposed to be like that. And also already on one hand, automatically flag bad data. And then once the data is calibrated, we also want a summary, or report on how much time is actually usable on this track, what RMS noise levels have been reached, etc. And then also have a first quick and dirty analysis of the science result, which means, is the source detected? Are we close to the goals of the proposal? How is the quality of the map in terms of UV coverage? Is it enough to get a good map? And then also, of course, are the science goal met or not? And I want to stress one thing. So since this work on the pipeline has been done in a systematic way, we only have mainly one person working on this with half. So since we are all astronomers, you have half the time that we can use for science that has been working. I find this kind of, yeah, worth mentioning.
Sorry to interrupt you. 10 minutes.
Okay. So the pipeline, as I mentioned before, is written in the Gildas language, which is in-house language that has been created and written since the early 90s and been upgraded ever since. It's a Fortran-based language. It's mostly developed by astronomers, not software engineers. So as I said, it has a different aspect than like what you can see from PMS and the observing setup system. It's debugged on the fly, so we are learning a lot. So it's a lot learning by doing, which is especially true now with all the upgrades. The better we learn the different aspects of the interferometer and of our new instruments, the better we can adapt the pipeline as well. Like with doubling the, for instance, just to give an example, so with doubling the bandwidth of the correlator, there are certain aspects to calibrate this part that is frequency dependent is a lot more challenging than if you have a small size of the bandwidth. You have to take into account the spectral index of the continuum emission of the calibrators that you're actually using to calibrate your data, which involved a huge rewriting of the pipeline to account for that and to make it to take this into account. And then also we are learning, since we want this to be fast, we are always learning more in how to optimize the different calibration steps and what to do. The pipeline will actually create an 80-page PDF output that contains all the calibration course and the useful monitoring products, which can be the pointing and focus behavior of the antennas, the tracking, the delays that we might be seeing. Of course, we need to know what the weather conditions were like, the receiver parameters, so the receiver temperatures, system temperatures, how the correlator was behaving, and there's a lot of things that go into that. And then we have, after that, we have certain add-ons that I call add-ons for the scientific assessment. So we have a detection assessment running that looks for, in the final calibrated data cubes, looks for sources, for lines. We have a Mosaic assessment because that's still, we are seeing, actually in the past few years, we have been seeing more and more large-scale mapping projects, which is a bit different from simple detection projects or single feed mapping projects, which especially for the AODs to assess whether a project is done or not. This includes a lot more knowledge about the track. And then those scripts, of course, they use mainly the Gildas software, but also we are more and more using Python, which is a lot used for bookkeeping for the tracks, how many tracks have been observed, how many files, to relay this to the status manager, to the observing scripts, and to other things as well. And it's to, everything is developed to help the AOD make a quick and robust decision on the track and the project. And then just to quickly tell you something about the actual calibration, where I also already described a bit what we are doing. So we have 3 different parts, if you wish. There's a first part that is done online during the during the observations at the telescope, which is calibration with respect to atmospheric considerations, a first and quick online reduction, and then of course all the writing of the data to the disk. Then there's the second part, which is called, in this case, this is called the RDI system. Then you have the click part where you actually do all the bandpass calibration, the amplitude and phases calibration, so all the calibration that is necessary to get clean and correct data. And then you have the mapping part where you actually start and doing the maps, you're writing out the spectra and everything. So there are three main, and the pipeline mostly works in Click, and then with the mapping part. And we are always also starting to work on the mapping pipeline. So to give you an idea how the pipeline looks like, so this is the first page, which gives several general information on the observation, so which antennas were used, which sources were observed as a calibrators that will help to calibrate the data, how good were the actual different calibration steps. It will show you the accuracies of the fits that are done during the pipeline. Then here you can see that's actually the RF bandpass, so the phases and amplitudes as a function of frequency, which we need to do to get a proper and correct spectrum. Then you get information on the different positions of the sources in the sky, which can be very important to understand if there are problems related to slewing or pointing or whatever. So you have azimuth and elevation. Then this is a plot on the pointing and focus behavior on the antennas during the whole track. And then at the end, as I mentioned, there is already an automatic flagging procedure that is going on and tells you, okay, this track, obviously it was a bit crappy. There was the atmosphere stability was not good enough. So the phases are like a bit all over the place. So for optical as normal, this is where you have too much seeing. And then the script does an automatic assessment on which data is probably not usable, and flags this automatically, and then the IDE can check, okay, this is reasonable, or this is too much flagged or not enough flagged, and go back. And but it's very robust. We have now something that is working very well and gives us very robust data that are reliable. And then just to show you about the pipeline execution times. So as I said, we want the pipeline not to exceed, or only in very exceptional cases, not to exceed an hour. Which in most of the cases, of course, with increased number of antennas, increased number of bandwidth and spectral resolution. And there are sometimes projects that need a higher sampling rate of the data. So in standard, our scan lengths are about 45 seconds, but we have seen that for certain projects, it makes much more sense to go down to 15 seconds sampling rate of the data. And then, of course, the pipeline will run a lot more because it has a lot more data to work with. That is shifting more and more towards the higher, but longer execution times. But of course, we are constantly working to improve that. We have, of course, now also more powerful computers that help us with having quicker reductions. But we are seeing that of course, the increased file sizes are more of a challenge today than they were before. And so before Polyfix, the sizes of the actual data files were about a couple of 100 megabytes, of course, depending on the tracks, but now it can go up to 100 gigabytes, which is 102 orders of magnitudes higher than it was before we have Polyfix.
Just 2 minutes, just 2 minutes.
Okay, okay, I need a couple more slides. So, okay, just to say, okay, we have increased the number of channels by a factor of 10 or more, which of course means that also all this online calibration that I was showing before, that takes a lot longer. And a lot of effort was put into to help fasten this up, speed this up. And then I want to finish to show you some plots for the detection assessment, what we are doing. So the data cubes are searched with no input parameter whatsoever to look for sources, whether in continuum or line emission, and then to have the highest, the strongest source inside the spectrum. It gives information about the tracks, the previous tracks that were observed and the last track that was observed, which is very important for the AUD to know. It gives a summary of all the different tracks and where there are detections found in the whole data cube, so in both the upper and lower sidebands. It gives an information about the whole spectrum, and then where all these detections were found within the field of view of the observations. And I just want to spend a minute maybe on the Mosaic assessment, because that's a very complex a thing as well for us. It's very difficult to schedule, especially if it's huge mosaics with 100 mosaic fields, or so several arc minutes of field of not field of view, but the size of the area that they want to map. And it's very important to know for the EADs if we have an equal distribution of the observing time spent so we have an information about how the mosaic was set up. And then we have several information about the RMS noise level distribution among the different fields, the time spent on each, and we are currently working on automated procedures that then recognize which of the fields need more time and which not. And then again, a summary of all the different tracks that were observed. Yeah, and I want to finish with the improvements and updates that we foresee for the near future. I showed a detection and mosaic assessment. We are currently working on something for mapping assessment as well that helps to the AOD to better and more quickly assess like if the view coverage is good enough, so we don't have to deal with too many side lobes, what the best combination of the different configurations that were requested in the proposals are, because it can always happen that we lose one of the antennas, or at the end, towards the end of the track, the weather conditions went bad. Then we are more and more trying to observe self-calibration projects that do not need such a good atmospheric phase stability. We also want to improve our line service, where we can switch much faster within one track between, so to have 32 gigahertz instantaneous instead of just 16, which allows to reduce telescope overheads. But of course, this also includes a lot of development on the level of the calibration. In the future, also, we plan to do dual band observations, so to observe, for instance, at 1mm and 3mm at the same time, as we did in the early 19s and early 90s and 2000 years, which we abandoned afterwards. And as I mentioned at the beginning, the final idea is also to have everything web-based for the PI. So from the proposal up to the end of the data, the delivery of the observed data, that I can check at any time through the system what state the observations are, if has there already been data taken on the observation, what kind of quality was the track. So that's the final idea. I mean, even though this will take a bit more time. And then, of course, the biggest challenge for us is not that we have missing ideas. We have many, many ideas, or the technical capabilities or capacities. It's rather that we have not a huge amount of stuff to do all of what we want, and in a reasonable amount of time, I guess, is something that everyone knows. And then I would like to thank you for your attention.
Thank you very much. Now we've got time maybe for, there are 3 questions, but we've got time maybe to answer one of them, and I will post the rest of them, the ones that were being asked on Zoom, on Discord, so we can continue discussion there. So the first question that appeared was from Hanno. 1 million lines of code in a language that is not commonly used sounds like an awkward design choice. How do you make sure that your code is, sustainable? Because you said that you've got an in-house language. How do you make sure that it's sustainable code?
Well, that's actually a big challenge. It's true that we want to make sure that it's also backwards compatible with all the upgrades that have been done. So we have a full group that is working on that. That's trying to keep it up to date, to keep it. I mean, already changes in compilers and stuff that changes in the. Now we have a lot of different operating systems, which was not the case like this like 10 or 20 years ago. So that's for sure, that's a big problem. So, and again, it's a question of staff and manpower, that we are currently, everything that is reduction, we currently only guarantee on our own computers, because it would take too much time because if there is a difference in the computer structure or the compilers, we have seen that this can relate into or translate into difference in the reduction. So to be sure that we really produce the best and the most reliable data calibration, we currently doing this part only in-house on our own computers. So people, well, currently we don't allow any face-to-face, of course, due to COVID. Normally people come here to calibrate their data. Currently we are all doing remotely, which is actually working very well. In the future, we want to go back to to a software that can be installed anywhere, and where people can actually reduce their data at home, or maybe we are going to a phase where we only provide reduced data. That's still under a lot of discussion. The part of the software that is compatible with all different kind of environments, that's a mapping part. And that's made sure, so it's being tested by our software engineers or our astronomers that actually work on the software that is working on different kinds of computers and everything. So that's for sure a challenge, but a lot of work is put in that it's kept being reliable and sustainable. Of course, what will happen in 5 or 10 years, we don't know, but a lot of effort is put into that. I hope this answers the question.
Perfect. Thank you very much. I've posted the remaining questions on Discord, so we can continue discussion there. I don't want to eat too much into the break. So now, yeah, thank you very much for your talk again.